As we are now recording, let's get the slideshow set up from the current slide. And my memory has it, my mark was that we were just at the beginning of 12.1. We had done the little introductory thing, and we were starting to talk about vectors in the plane. And what we're going to try to do is go through this pretty quickly. How are you on vectors? Familiar with them? It's been a while, or? Okay. Well, we'll take the time we need then. Because you haven't had physics yet, have you? Okay. A lot of times by the time Cal 3, folks have already had physics, so we can sort of breeze through this. We'll slow down a little bit. Okay. What we're talking about here is a two-dimensional vector in the plane. Okay? Now, what a vector, and by the way, vectors in your text are sometimes given just a symbol. And let me get my, as soon as I go to write, it's going to shrink. Well, it's not shrinking. I don't know why. There it goes. Okay. Let me get my pen back to a dark color. Here we go. In the text, vectors are represented by a bold letter. I don't write bold, okay? It's sort of hard for me to write bold. So what I always do is put the arrow over it, okay? That symbolizes a vector on the board now. In the text, it's going to be a bold V. So a two-dimensional vector V, determined by bold V in the text, arrow over it on the board, is determined by 2 points in the plane, an initial point, usually P, and a terminal point, and by the way, the initial point is called the tail, or the base point, and the terminal point Q, which is then called the head, okay? So one way to write V, vector V, would be PQ, and put the arrow over that as well. Now this has meaning here. The tip here is for the terminal point, the initial point of this arrow, that's for the initial point of the vector. So PQ always means it starts at P, ends at Q. Head, tail, okay? So that, or did I say that backwards? But anyway, just like this, okay? So there's a vector PQ. Now this has specific points with it, but any vector V, and in the text, they'll put the arrow over this to indicate that, but they usually just bold this. I have to put the arrow over both of them, so you can tell I'm talking about a vector. Okay. The tail is the P, and the head is the Q. And, okay, we can draw a vector as an arrow pointing from P to Q, just like they've done here. Pointing from P to Q. If P's at that end and Q's at the pointed end, this is the head here, the tail there, okay? Pointing toward Q, okay? Now, that vector is said to be based at P. I usually don't use that terminology. And it also shows the vector with a terminal point 2, 2, initial point 2, 2. Did they say that wrong? Did I read it wrong? Initial point 2, 2, P 2, 2, terminal point Q 7, 5. Okay? Now, we haven't named it yet, but we're going to. But in this text, vectors are represented by bold-faced lowercase letters such as V, W, A, B, whatever, as long as it's bold. When I write it, I have to put the arrow over it. Okay. Said that enough times, right? What do we mean by the length or the magnitude of a vector V? Well, we symbolize that by putting the vector V, but then putting like double absolute value bars. Now, different texts will use different symbologies for this, but this is the most common, okay? This is called the magnitude or the length of V. That's the distance from P to Q. Now, do you remember how to do distance? Yeah, Pythagorean theorem, okay? Okay, this distance here, this length here, magnitude of V would be the change of X. This is the change of Y, and this would be change of X squared plus change of Y squared is equal to magnitude squared. Okay, that's sort of weird the way I've written it, but yeah, that's how you do the magnitude. Now I'm jumping ahead. They haven't gotten there in the book, but I thought since it was there we would do it. So now, what if we had another vector? This one we're going to have this initial point at the origin, not at some random point P somewhere on the plane, but at the origin. Then we can call this the vector OR because the origin is O and R would be the terminal point. Now that could be a P up there, a Q up there, or whatever. This is they use P and Q here, they just use R there. Now, this is and they call this a position vector. This is what we usually call a vector in standard position, where its origin is at where its initial point is the origin, and this would be that position vector OR. Now that one has to be terminating at 3, 5. Doesn't have to; it could be anywhere. But anyway, there's a vector V, and this can also be called V. This, we can call that V as well. It's not the same as this other V, but they're just like everybody's favorite variable is X. Everybody's favorite vector is V. Okay, they have W's and U's and things like that too, but when they fall down to it, they'll get to calling it V. Okay. The vector V, whose points from the origin to the point R, is called a position vector of R. That shows the position of the point R, okay? And that would be at 3, 5. So here's some vector terminology. Two vectors, I think we'll go to a different slide. Two vectors, V and W. I may have to write in a second, but at least for now, let's blow this up. Boom. Okay, two vectors, V and W here. Of non-zero length. Now, you have to have it, okay, but it's really almost a little ridiculous. You have to define something called the zero vector, okay? Now, a problem, one of many problems with the zero vector, usually we say a vector has a magnitude and a direction. The zero vector has no magnitude and no direction. Okay, so it's hard to call that a vector, except we have to have one. So when we're talking about any other vector, we have to say the non-zero vector. So V and W are both non-zero vectors here, meaning non-zero lengths, and they're called parallel if the lines through V and W are parallel. And obviously in this case, this V and that W, at least by all appearances, those two lines are parallel. So these two vectors are parallel to each other, okay? We also say, well, and all those vectors are, they just didn't name one of them W. That's parallel to that. Of course, these two lengths are different, but the directions are the same. Here, the directions aren't even the same. They're anti. One's exactly the opposite of the other, but they're still said to be parallel. In some technical way, you might call it anti-parallel, meaning exactly the same direction but in opposite. Exactly opposite directions but parallel lines. But this book is called in parallel. So all those are parallel, these are parallel. Another thing you can call is that W is a translate of V. In other words, you've taken the vector V and moved it without changing magnitude or direction. You just translated it to a different place in the plane. Now, in that case, V and W are identical vectors. Same magnitude, same direction. Up here, they're not. These are obviously not same magnitude, though they have the same direction. These look like, well, no, they're not even same magnitude. But even if they were, the opposite directions, they would not be translates of each other. Okay, just some more terminology. Okay. Parallel vectors can point either in the same or opposite directions, like I said. Some places will call those anti-parallel, but this book is not. A vector V is said to undergo a translation when it is moved to begin at a new point without changing either the length or direction. The resulting vector W, as shown there, is the translate of V. And except for here, seldom seen that terminology used, but it is correct terminology. In almost all situations, it is convenient to treat vectors of the same length and the same direction as equivalent vectors. Okay? Those two, V and W, they're translates of each other, they're equivalent vectors. We even say they're equal to each other, though they're obviously not the same vector, but they are equivalent to each other. So what do we mean by that? And even if they have different base points, well, V and W are equivalent if W is a translate of V, like I just said here. Every vector can be translated so that its tail is at the origin, making it a position vector. Therefore, every vector V is equivalent to a unique vector V0 based at the origin. Let's see if this next slide shows that. Yeah. Okay. Again, just basically our basic nomenclature. Okay? These vectors are all translates of V, so they're all equivalent vectors of V, meaning same magnitude, same direction, nothing changed. If one of them had a point that way, that would not be a translate. Equal magnitude, the opposite direction. So to be equivalent, exactly the same magnitude, exactly the same direction. These two same direction, different magnitudes. This one possibly, I would say, I don't even think that's same magnitude, but different direction. They're not equivalent vectors. However, here's one. There's a V, and here's what they call V0 because it's starting at the origin, O, the origin. So it's hard to tell whether that's a 0 or an O. I usually call it V0. You could say VO for origin. Unique vector based at the origin equivalent to V. So you could call that a position vector if you want. Okay? Just nomenclature so far. To work algebraically, we define components of a vector. Here is the way to deal with vectors. Okay? You can deal with magnitudes and directions, that kind of stuff, and you have to. It's essential in some circumstances. But whenever you can, the easiest way to deal with a vector is in component notation. The components of vector V, there's that bold letter V, I would have an arrow over it. PQ, P being the initial point, Q being the terminal point, where P is A1B1 and Q is A2B2. Okay? Now, sometimes books will call this A0, B0, and A1B1 there. It doesn't matter. There's just subscripts. They don't really mean that much, except the ones stay together and the two stay together. Okay? So the components of that are components of that vector PQ, where P is this and Q is that. The A component is A2 minus A1, final minus initial always. That's the X component, and the Y component, or the second component, B component, you might say here, B2 minus B1. Okay? That gives you the component notation. So that pair of components is denoted by angle bracket AB, close angle bracket. So in this text, when you see an angle bracket, that means vector. In your linear algebra text, we haven't gotten there yet, but they write vectors as parentheses AB, just like a point. And that is somewhat confusing. And the bizarre thing is that same author for linear algebra, we use his pre-calculus algebra and trig text, and in the trig part, he uses this notation for his vectors in that text and uses parentheses in the linear algebra text. Bizarre. okay? And you'll hear me fuss about it because I always tend to put vectors in angle brackets, but he doesn't in that one, so I try not to, and then I'll get it all screwed up. Okay, so that's how we refer to components of a vector. Okay. And here we have the Silva. All right. We're on page 626 in section 12.1. We just defined the components of a vector, and here we're going to illustrate that. Okay? All right. Here we have some old vector v up here. Initial point a1 at p at a1 b1. So the x component, y component. Okay, this would be a1 right here. This is b1 right there. And here we have point q, which is a terminal point, a2 b2, where a2 would be here, b2 would be up here. So that's vector v. Okay. Now, the other way to refer to this, rather than PQ or V, we could refer to it as if it was in the standard position, back with P being at the origin, and why in the world did they then call this P0? If they're calling this P up here, I would have called this Q0. But they didn't, they called it P0. Which is fine, you can call it anything you want to, but it just seems like it's crossing up your nomenclature. But the component of this vector would be, of this vector up here, is a2 minus a1, which is this length, comma, b2 minus b1, which is that length, b. And if you translate that down to the origin, a units on the horizontal, b units vertical, that would be the point they're calling p0, which is ab. This is equivalent vector, or a translate of that one. They have the same components, AB, so technically they're equivalent vectors, but quite often we'll say they're equal vectors. Okay, we'll use that equivalent and equal as if they're the same, whereas sometimes there's a little bit of a little distinction you make between those two. Okay? Now, I've already given away this one. Whoops. Hit the wrong way. Quit. Okay. Hit the wrong button. All right. We mentioned earlier the magnitude of a vector V, denoted by the two double lines here. Okay? Sort of like a double absolute value. That's not what it is. This is not a vector. This is a magnitude, a length. Okay? By the way, lengths are always positives. Okay? Just by definition. A length is a positive value. Just like an absolute value is always a positive value. Okay? So that's why I mentioned that terminology is sort of like that. By the way, in case either of you had noticed, and if I just found myself rubbing it, trying not to, but I had a treatment on Friday, which sometimes does, does do something to my immune system. And then Saturday I was working outside. A beautiful, beautiful day. Worked outside just about all day long, and was dealing with stuff above ground and getting stuff probably blown into my eye, pulling up roots and weeds and things, and may have gotten something, sweated and got something. Somehow I got conjunctivitis in this eye. So if it looks bad, it is. But sometimes it'll get really hurting and it's hard to focus. So if I start calling something wrong, just correct me. That's what's going on. Sorry about that. So magnitude of this vector V, which you could also the magnitude of PQ. If you wrote it as PQ, then you expect this to be A2 minus A1 squared plus B2 minus B1 squared. Because then you would expect these to have different components. But the component of the vector is still A and B, as we saw earlier. And here's the thing that's interesting about it. for magnitude purposes, it doesn't matter which one you call point 1 and point 2. You could have done a1 minus a2 squared plus b1 minus b2 squared. Or you could have even reversed it. It's not a good practice to do that, but you could because you're squaring it, so it doesn't matter which one's the larger or smaller. You're squaring it's always a positive quantity. Add two positive quantities, that's positive. You take the principal square root, that's positive, so the magnitude is always positive. With one little exception. That silly thing that they call the zero vector, then its magnitude is 0. It's not technically positive, but 0. We're going to assume most of the time they're non-zero vectors. Okay. Okay. So the base point, if you put the base point P at 0, 0, and the components V are then just the coordinate endpoints, A and B are the endpoints of Q, just like we saw in the previous slide, the length of a vector in terms of its components, and that's by the distance formula, as we said a little bit earlier before you came in, Silva, that's what you get. The zero vectors whose head and tail coincide, they're the same point, is the vector, and we denote that. They denote it as a bold 0, and I've got to, why this is not shrinking when I hit the key. There we go. I don't know why. Saying something about the zero vector. Oh yeah, they represent as a bold 0. I put it 0 with a line over it. That's different from the number 0. Okay. In fact, the zero vector is a vector whose components are 0, 0. That's the zero vector. Those are the numbers 0, 0. This is in 2 space, by the way. And the angle brackets indicate it is 0. Okay? That it is a vector, sorry. And it has length 0, and it's the only vector that has no direction. And technically, it has no length either. The length is 0, and the direction, it has no direction. It could be pointing any direction because it has no direction. I mean, the 2 points are coinciding with each other, so it really has no direction at all. Okay. In this text, the angle brackets are used to distinguish between vector V, which would be A, B in angle brackets, and the point P, which would be the terminal point AB. Those would be in parentheses. That indicates a point. Angle bracket indicates component. Okay. So get even the words sound alike. They're coordinates of a point, components of a vector. Okay. So when you see the angle brackets, the numbers or the letters or whatever is representing there are components of the vector. When you see parentheses, they are coordinates of the point. Okay. Now, it says here, some textbooks denote V and P both by parentheses AB, and then you just have to tell it by context. This book doesn't. When referring to vectors, we use the term length and magnitude interchangeably. The term norm is also commonly used. We haven't gotten there yet. We'll get there a little bit later. But for now, length and magnitude are the same. Goodness, I just started aching. Sorry. Equivalent vectors have the same length and point in the same direction, but they can start at any base point. Okay? In other words, their components would be identical. And you can't tell where the base point is. All you have is the components. So let's do example 1. Well, maybe it does have. Nope. All right. A little blurb here that's not in the older text, I don't think. The older edition. What's that? I can't hear you. Oh, yeah, no, okay, that's right. I said it backwards. It's in the older text. It's not in the new text, sorry. But it says this: we assume all vectors are based at the origin unless you're given another base point, unless it's otherwise stated. That's not given in the new text. It is in the old text. Sorry, I said that backwards. Okay, so let's see example 1. I think this is example 1. All right. Determine whether V1, this is vector V1, this one right here, okay, and vector V2, that's this one down here, and this is P1, Q1, this one's P2, Q2, are equivalent vectors, where P1 up here is 3, 7, Q1 is 6, 5, P2 is -1, 4, and Q2 is 2, 1. How can you tell whether those are equivalent vectors? Can you look at them and tell? I don't know. My vision isn't that great. They look pretty close to being parallel, but something makes me think they're spreading a little here, but maybe just the distortion of our projector or something like that. And then, too, looking at that, it looks like that might be just a tad shorter than this. So, on the up front, I would say they look like they could be equivalent, but I can't tell for sure. Okay? How can you tell for sure? Write them in what form? Always the preferred form. Component form. If you get them in component form, everything should become a lot clearer. So let's do that. What would be V1 in component form? Your horizontal or x component would be yeah, and you always do the q minus the p. The components. 6 minus 3 would be 3, comma, -2. So there are your components of vector V1. Let's do the same thing for vector V2. What would be its components? 3, so far so good. -3, off by 1. So those two are not equivalent vectors. Like I said before, it looked like V1 was a little shorter than V2 just by looking, but when you do component notation, you see you got it. Nailed. No way around that. Okay? So component notation, that's the way to deal with vectors. Anytime you can, use component notation. All right. Okay? So first, determine if they're equivalent. No, they're not. Okay? The second says, what is the magnitude of V1? So we want to do magnitude of vector V1. And what would that be? Would be the magnitude of V1? A little louder. Okay, which would be 3 squared, which would be 9. And here's Marcus. Get you in here. All right, just missing one, Faith. Both classes this morning, each one, we're missing one person. Hopefully we'll get this one in. Okay, and what's the last part? Okay, we're doing example 1, bottom of page 626, top of 627 in section 12.1. What did you say? Sorry, I interrupted. I can't hear. Okay, and what would that be? -2 squared. And that would be the square root of 13, you got it. There's the magnitude of V. And we got perfect attendance. Ding, 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 ding. All right, way to go. Good thing, T. Okay. We just finished example 1 in section 12.1, bottom of page 626, top of page 627, square root of 13. Now, I could see and hear Emmanuel going through all the technical definition of how you got the magnitude, but here's the easy way. Once you got it in component form, you don't have to do subtraction anymore. You already got it. First component squared, what's that? So it's a lot easier. Once you got it, that's why component form is the way to go. Most of the time with vectors. You know, if you got it in that form, everything pretty much is easier to do. But if you weren't given component form, yeah, the way you did it was absolutely correct. The square root of 6 minus 3 squared plus square root plus 5 minus 7 squared. Get you something. All right, any questions on that? Okay, let's move to example 2. Now, this I don't think is the same one.
So we don't have to find the magnitude of V2?
They didn't ask for it. We could find it. Let's do it. What's the magnitude of V2? You asked for it. You got it. Toyota. Okay, and that would be square root of 18, which we could call 3 root 2. You don't have to, but you could, because 18 is 9 times 2, square root of 9 is 3, and you're left with the square root of 2. Always positive. Magnitudes of vectors are never negative. Could be 0 if you had a 0 vector. Other than that, always positive. Always. All right. Good deal. Ready for example 2. All right. Now, example 2 says to sketch. And for the 2 who just came in, because I just caught myself doing it again, I have conjunctivitis in this eye, and it really, right now, it's just a little itchy. Every now and then it'll just start paining, and sometimes it interferes with my vision. So if I get wacko here, you know, or misread numbers, that's probably what's going on. Either that or I'm just wacko. Okay. All right. What I think I'll do is clear, goodness, it's hurting, all the ink from this slide. Sketch the vector V, which is 2, negative 3, based at P, which is 1, 4. Now, I can use the graph that's here. So let's get the base first. Where is 1, 4? How would I get there? That's 0.14. Right 1, up 4. There's my P. Okay? Now, it says sketch the vector from that base point, P, 1, 4, the vector 2, negative 3. So where would I go from here? Two, negative 3. Okay, it goes to the right 2, so that winds up over here at 3, but down 3, and we were at 4, so it goes down to 1. So it's going to be at 3, 1. So there is the vector. Did they give it a name? Yeah, there's the vector V, which is, and I just messed it up. And this book, for those who came in a little late, does use angle brackets for vectors. Okay, so this vector is 2, negative 3 from the base point of, I thought I put that in here, I guess I didn't, and that was 1, 4. That's your P. Okay, now parentheses means components, no, coordinates of a point angle bracket means components of a vector. So this is the point P at 1, 4, parentheses around that. And this here, the vector representation is the vector V, which is 2 to the right and down 3 from that point P. Okay? Does that make sense? All right. So it has a terminal point at Q is at 3, 1, which we've already indicated. So this Q is a point, so it's parentheses 3, 1. Okay. Okay. So it says sketch the vector V 2, 3 based at point P 1, 4, and then sketch the vector V0 equivalent to that V but based at the origin. So how would I do that? How would I plot or sketch V0? Start at the origin and go down to the point 2, 3, 2, -3. Okay, right 2, down 3, and draw the vector in there. This is vector V0, which is equivalent to vector, mine doesn't look like I've got too wide there, but that's the equivalent vector. Okay, but this is a position vector because tail is at the origin. So this is vector 2, 3. Vector V0 is also at vector 2, 3. It's just that this one has a terminal point of 2, -3, 2, -3. So this vector is also 2, -3 in vector notation. Angle bracket 2, -3. But this point, and they called it P0, I'd just as soon call it Q0, and that terminal point there would be the point 2, -3. Now, I put all that up there just to illustrate. Vectors have the angle brackets. These are components of a vector. Points have parentheses. These are coordinates of the point. Just so you get the nomenclature right. All right. Any questions on that? Okay, now, they have this in the text too. Let's see. Yeah, there they are. Why didn't I go there? Oh, well, actually, I wanted you to think through and work it out before you saw it because I knew they were going to just give you the answer. Okay, so here's your initial point, base point, 1, 4 for this vector V, and you go right 2 and down 3 from that to get vector V. Angle bracket 2, -3, winding up with a terminal point. You go 2 over from here, that gives you 3, and you go 3 down from 4, that gives you a 1. So this is the vector V, 2, -3. And if you translate that down to an origin, so you're in standard position, your position vector, then your terminal point down here is also going to be parentheses 2, -3, but then when you connect that with the line segment, directly line segment, that makes your vector V0 2, -3 as well. Have the same components, different base points, V0 being your position vector, so its endpoint is the same, has the same coordinates as the components of the vector. Okay. Now, I think we can move to vector algebra. Okay. Now, what's the things can we do with, say, real numbers? What operations do we usually incorporate? So, 4 basic operations in mathematics. Adding, subtracting, multiplying, and dividing. Okay? we're not going to do, we're going to add and subtract first. So the vector sum of two vectors. Here's some old vector v just hanging around here, and there's another vector w. Obviously different directions, I think different magnitudes as well. Now what do we mean by adding v to w? Now the way they've drawn them here, which is very common in physics, these are two forces acting on that same point. One force in this direction, one force in that direction, one force that magnitude, one force that magnitude. This is how we'd represent it. But if we wanted to come up with the total force acting on it, we have to add these two vectors together. Well, they don't add very nicely or clearly when you do them from the same point. So what we do, we take w and translate it up to the initial point of w to be at the terminal point of v, and add v plus w, and that gives you the, and they call this w prime. It's the same as w, it's equivalent to w, same magnitude, same direction. Move it up to here, and then your resulting vector will be v plus w, sometimes called r, but here they just call it v plus w. Okay, so I'm not really too fired up about calling that w prime, except they're just saying it's a translation of w. But here's the key. What if we took v and put its tip on the tail of w, and you get the same vector, v plus w. And they show that here too. Here is vector v, w or w prime if you want to call it. Here's vector w, that would be v or v prime, equivalent vector there. They come to the same point. And because of the rendition of this one, we sometimes call this the parallelogram law. If you're drawing vectors, this is how you add them geometrically, by drawing. Not the way to go, okay? It works okay if they happen to have come up right on tick marks, you know, of your hatch marks there. Yeah, you can do them this way. But if you have fractions and variations in them and stuff, this is a miserable way to try to do it, okay? There's a much easier way. Anyone want to make a guess what that way will be? Adding them by components. Everything with vectors, I think, are better when you use component notation. These are nice, pretty pictures showing you what happened, but in reality, use your components. Much easier to do. Okay? Now, this parallelogram law works only when you have two vectors. Other than this, you have what they call, or they don't call it, I would call it a polygonal wall, okay? In other words, drawing polygons if you have more than two vectors. So let's say we're adding these four vectors together, v1, v2, v3, and v4, okay? So let's start the way they said, start with v1, and then translate v2 so its tip is on the tail of v1, and then translate v3 till it's up there. I don't have long enough fingers to do it, and then come down with v4, and sure enough, that's what you got. You start with v1. Now, why they call it v1 prime, it's the same as v1. Translate your v2 till it's tip to tail there. So it goes there. v3 is as long as here, it goes up there. And then v4 is as short coming down there. And do tip to tail, tip to tail, tip to tail. And then from the tail of the very first one to the tip of the very last one, that's your resultant vector, v. Okay. Now here's the interesting thing about this. By just looking at this, I would say v, I'll definitely say this. V is shorter than the sum of the magnitude. The magnitude of V is less than the magnitude of all the others added together. Would you not agree? Because magnitudes are always positive, you would be adding this length to that length, to that length, to this length. Yeah, no way, okay? Occasionally, that will be equal. Never will it be greater than, okay? The only time it's equal if V1, V2, V3, and V4 are all in the same direction, parallel to each other in the same direction. When you add them together, you'll get a vector exactly equal to the magnitude of all of those magnitudes. But if they're not, as in this case, they're going in different directions, the resultant vector is always has a magnitude less than the sum of the other magnitudes. And not just that, but hard to say here. Looks like to me V could be actually less than or awfully close to the same as V2, and definitely less than V3. So the resultant vector doesn't even have to be as long as any of the other vectors. It may be shorter than them all. In fact, it could even be 0. Okay. If you had maneuvered this around and your final vector was like this, actually shorter than that or any of the others, then that is still your same vector. So in real numbers, if you're adding negatives to positive, you can come out with a smaller number. Same thing here. You're not adding negatives, but you're adding vectors in different directions, so your resultant magnitude could be less than any of the ones going in, or some of the ones going in. All right, so that's how you add. And I wouldn't call this the parallelogram law. That's definitely not a parallelogram anymore, but it would be a polygon. So I call this polygonal way. Now, so that's how you add vectors. Seemed like to me we ought to do subtraction next, but they're not going to. We're going to jump to scalar multiplication, then come back to subtraction, and there is a reason for that. Nope, sorry about that. The new edition does scalar multiplication. The older edition and the slides do subtraction next, and then go back and do, well, I don't know where they do scalar multiplication. Yeah, they do it next, okay? So, we'll come back and do the subtraction in a minute, okay? This is when they start talking about scalar multiplication. No, I'm sorry. I wasn't reading the book. I was just looking at the pictures. They do subtraction next. So let's do it, just to keep the order the same. Okay. Now, again, we're starting out with the same two vectors, V and W. This time we're doing V minus W. This is why I thought we were going to do scalar multiplication first. What do we mean by minus W? Well, this is W. Negative W would be the same, along the same line, but in the opposite direction. In the same line, but in the opposite direction, that would be negative W. So V plus a negative W would be V minus W. That would be to take negative W, put it up here, tip to tail, and this would be your resultant vector then. V minus W is the same as V plus the opposite of W. The opposite of W just puts it in exactly the opposite direction along the same line. Now, more simply, V minus W is the translate of the vector pointing from the tip of W to the tip of V. If that's something that speaks to you and you say, oh, now I see it, fine, use it. To me, that's harder to remember than this. This makes more sense to me than trying to remember which one is the tip and which is the tail. Do it out and it shows it to you. But either one of these is fine. V minus W would then be from the end of W to the top of V, translated to the same place, origin, and that would be vector subtraction. To me, this makes a lot more sense. V plus the opposite of W. But you see, there's no new rules. It's just adding the negative of the second one. And once we get into component notation, everything is so much easier. I wouldn't worry much with this, okay? It's all easier. Now we do scalar multiplication. All right. Now what do we mean by that? Lambda, why they chose lambda, I guess there's a reason. No particular one, though. It's just a number. Quite often they use the symbol C, not lambda. Why they didn't in this case, I'm not sure. Just about everywhere else they will. But lambda times some vector v. Basically what this is doing for you, since lambda is a scalar, and scalars are just real numbers. Real numbers can either be positive or negative, right? Or zero. We'll not go there, but it could be. Okay? And since that could be a negative number, we put the absolute value of lambda times the magnitude of v. So the magnitude of this new vector, lambda v, is equal to the magnitude or absolute value of lambda, which is just a number, times the magnitude of v. Keeps everything positive always. Okay. So there's a definition, and this is a form, or is leading to, scalar multiplication. Okay? Now, here is their graphical representation of it, and as you may guess, this is not the best way to do this. The best way to do it is by components. And if you do it by components, to me it all makes so much more sense and is much simpler to wrap your head around. So here's a vector v, that's the red vector here, and the vector 2v, or not 2v, okay? And that's the longer, bluer vector here, okay? They're both based at the point P, but 2v is twice as long as v, okay? They're parallel. They're based at the same thing. They're going in the same direction. But now vector v and minus v have the same length. Remember, length and magnitudes are always positive, so you don't say this is a positive length, that's a negative length. No, lengths are always positive. So these two, even though they're going in different opposite directions, they have the same length or magnitude, but they're going in opposite directions. These two have different lengths, but going in the same direction. That would make the second one twice the length of the first. Okay? Because we said it's 2d. And this is minus 2. You're just negating it and going from that direction. Same line, but opposite direction. All right. Now, if you're doubling the magnitude, you're also doubling the x component from 3 to 6, doubling the y component from 3 to 4. That doubles the hypotenuse of the length from d to 2d. Does that make sense? That is sort of weaseling your way around to getting what scalar multiplication is. Okay. So I guess, let's see, are they going to have another slide? No, let's go back to this one. The magnitude of lambda is called the scalar, the scale. You're scaling up v. If v was a certain length and lambda was something greater than 1, you're scaling it up. You're multiplying all the components of v by that lambda. If lambda was a number between 0 and 1, you're scaling down on that. So the magnitude of lambda v would be less than magnitude of v was to begin with if lambda is between 0 and 1. Now, of course, if lambda is 0, you've gone to the 0 vector, which is kind of wacko, but it's okay. If lambda was negative, it doesn't matter because you're multiplying by the absolute value of lambda. Okay, that's the thing that scales up and down. That's why they call it a scalar. Okay. I think we've already hit those slides. Figure 11 doesn't show up on the slide set here, I don't know if it's, do you have a figure 11 in your book? Right, okay. You go back and find, yeah, I can write it here.
You said the three figures.
What's that?
Three figures.
Okay. Let me show you what their figure 11 is. You may have one later on that's similar to it. Okay. This is our figure 10, and the next one, figure 11, shows it this way. They show a vector sort of going like this, and another vector sort of going like this. They named this one vector V, and that would be components A comma B. Vector W is here, and they will give this as components CD. Sorry, my eye is just almost beginning to throb, so losing a little bit of focus here. Okay, so if those are your two vectors, vector V, which is components AB, vector W, which are components CD, okay, and you were to add these two together, I don't know why they're repeating this, that would be some vector up here, and that would be V plus W, which would be W added this way or V added that way. Okay. Now, is that the same as yours? Okay. I don't know why they repeated it here. And then the B part, so all of you have the same one. Okay, I won't go into that. So it's there, it's doing the same thing we just did. It's just the second part, the B and C part, shows a scalar multiple, okay, of B, of vector V. But it's a different vector V from the one here. So to keep from going over that again, we'll just skip on over it since they didn't show it in the slide set. All right, let's do the vector operations, and this time, by all means, let's use components, okay? So much easier, so much more straightforward. You don't have to draw that nicely. It always helps, but you don't have to. You can just have the components here. All right, if V is some component AB, V is vector with components AB, maybe this is what that figure was. And W is CD, component CD, C for the horizontal, D for the vertical, X, Y, whatever you want to call it. Then if you're adding vector V plus W, don't draw parallelograms and that kind of stuff. All you do is add the first components, A plus C, that's going to be the first component of your sum vector, and the second component, B plus D, is going to be the second component of your sum vector. There's the way to go. You don't have to draw parallelograms or polygons or anything else, just add components. But be sure you keep the components corresponding, okay? And then even easier, just as easy when you're doing subtraction, you don't have to remember, well, which way am I going now, plus or negative W, nothing like that. Just add the component, or actually subtract the components. A minus C, comma, B minus D. It's just that simple, okay? You just do what the components tell you. Now, if you're multiplying a vector V by a scalar lambda, what do we do here? We multiply this vector V as AB, so it's lambda times A, comma lambda times B. It's not just by one of them, it's by every component. Okay? And then one final vector operation using the good old meaningless, almost zero vector, but you do have to have it. V plus the zero vector. V is AB. The zero vector is 0, 0, so this would be A plus 0, comma, B plus 0, which would be AB, which is the same as V. Or you could add the zero vector, 0, 0, plus the V vector AB, 0 plus A, comma, 0 plus B, AB, you got the same thing. That's your vector V. So your zero vector, if nothing else, is the additive identity element for vector addition. And for no other reason than that, we need that just to complete all of our features or characteristics of vector addition. The additive identity element. You add it to a vector, it stays the same. All right. Oh, here it is. Sorry about that. They did the block before they, on the slide set before they did the picture, or they did the picture in the book before they did the slide set. So here's what I was trying to show before, and this shows it better, cleaner, prettier than what I had it. Okay? And this just shows the two things we were just talking about. Even though they're showing it by the parallelogram method, if you look carefully, this is vector AB, A on the x-axis, B on the y-axis. This is vector CD. Now break that down into x component is C, y component is D. So what you have there is add the A component to the C component here, and you get A plus C. Add the B component here to the D component there, you get B plus D. All right. So the A plus C, comma, B plus D would then be this value here. A plus C on the X, B plus D on the Y, and that would be your resultant vector. So don't even worry about drawing parallelograms and that kind of stuff. Add your components. Okay? They did show subtraction, but it would work just the same. It would be A minus C, B minus D, if you were to do B minus W. They did show that. Now the second part, they show scalar multiplication. If this is your vector V, which is AB, different AB from here, but AB, A is the X component, B is the Y component. Goodness, that light hurts my eyes. If you're multiplying this by a scalar, you scale up the A and you scale up the B, lambda A, lambda B, and that isn't a doubling. It might be 1.3 or something like that. It makes it a longer vector, same direction, that it changes its magnitude. Okay? Now, if that lambda, had been a number, this lambda was a number greater than 1, because that magnitude is greater than this magnitude. Okay? If that lambda had been between 0 and 1, that would have been scaling this one back. You would have scaled back A and scaled back B, and that would have given you lambda B here. If the lambda were negative, it changes the direction. Okay? If it's a negative greater than absolute value of 1, it lengthens it in the opposite direction. Between 0 and negative 1, it shortens it in the opposite direction. The minus sign does one thing, and the magnitude does the other. All right, I think we're ready for example 3. Okay, then they show the difference of two vectors, and we had already done that too. Okay, example 3. For vector V, which is 1, 4, that's this one, okay? You're adding, and vector W, 3, 2, that's this one over here. it says calculate V plus W. Now, they did it with a picture. You don't need to do it with a picture. What is V? One, comma, 4 plus W. Three comma 2, and if you're adding those together, what do you get? I'm sorry. Yeah, that's what we're doing. We're doing A plus C. That will give you this one. What will that be? 4, comma, 6. Okay? Without having to draw a parallelogram, even draw a single vector. You didn't need that, but if you looked at it, you got the 1 here, that was from V, plus 3 here. So 3 more, and you get 4. And then the Y component started out with a 4 here, and goes up 2 more, and that gives you 6. So without having to draw anything, just add the components, and you got it. Components are the way to go. Okay? The B part says, what is 5V? Five times 1 is 5. 20. There's that new vector, 520. Huge, long vector. But yeah, you've scaled it up by a factor of 5. All right. Now they showed the vector sum, they didn't show the scalar multiplication that you can imagine. Okay. I think next is theorem 1. I'm sorry, but my eye is really feeling lousy. Okay. Theorem 1 addresses basic properties of vector algebra. So with all vectors U, V, W, for all scalars lambda, now, most books you see, this one uses lambda, which is fine, nothing wrong with that. The commutative law for vector addition, and we showed this with the parallelogram method, okay? The commutative law says if you add vector V to vector W, that's the same as adding vector W to vector V. I mean, if you add the components are just scalars. It doesn't matter which order you add real numbers, they come out the same, and so do your vectors. Associative law, and this is with addition now. Notice we're only talking addition here, okay, not multiplication. If you're doing addition, you could have 3 vectors, U, V, and W. If you add V and W first and then add U to it, you get the same result as if you had added U and V together and then added W to that result. And the reason is that you're adding by components. This would be V1, V2, this would be W1, W2. You add those together, you get V1 plus W1, V2 plus W2. Add that to U, which would be U1, U2. That would be V1 plus W1 plus U1, comma, V2 plus W2 plus U2. You get the same result no matter which way you do it. Now your distributive law for scalars, okay, and that really works out just as well, just the same. If you're adding 2 vectors together, V plus W, but then scale it up by lambda, that would be the same as scaling V up by lambda, adding to that to scale W up to lambda, and you get the same result there too. You just distribute basically the scalar across the vector addition, and it works. Okay. Notice these rules, properties are only good for vector addition. Okay. Subtraction, you know that doesn't work. V minus W is not the same as W minus V. That's not true with scalar numbers, with real numbers. It's not true with vectors. And the same type thing with associative, you just don't do it. You can do it with distributive, it works the same way. So a minus here, that becomes a minus there. So you can use that, okay? But don't try to commute vector subtraction. You can't do it with real numbers, you can't do it here either. Okay. Now, we're getting into another topic, which is a pretty important topic, okay? And this is linear combinations, okay? By the way, when they mentioned right after that table, they said these properties are verified easily using components, and basically that's what I talked through. That's what we were doing. All right, but now let's look at a concept called linear combination. A linear combination of two vectors, V and W, is also a vector, okay? But it's a vector that consists of some scalar times the first vector plus some other scalar by the second vector, okay? If V and W are not parallel, that's the only requirement here. Here's your V, the blue vector here, here's the W, the blue vector there. They're obviously not parallel, okay? And if they're not, then the linear combination of these two vectors, which is multiplying any old two scalars with those, okay? All right. R, by this drawing here, you can tell R is a negative number because it made it go in the opposite direction. It's also a number that's less than 1, between 0 and 1, because it scaled down the length of V, okay? S over here is a positive number because it didn't change the direction of W, but it's also a number between 0 and 1, because if it was greater than 1, it would be scaling up. Between 0 and 1, it's scaling down. And if you're talking about this U over here, a linear combination of RV and SW, that's a linear combination of the two vectors, V and W, then that's going to be somewhere over here, okay? So that vector U can be expressed as a linear combination of the vectors V and W. And in this case, R is a negative number, meaning less than 0, and also its magnitude is between 0 and 1. Okay? And S was a positive number whose magnitude was between 0 and 1. Now, coming up with another term here. This parallelogram that we have here, the sort of tan-colored parallelogram, P is spanned by V and W and consists of all the linear combinations RV plus SW with 0 less than or equal to R and S less than or equal to 1. Okay? So that means R is any positive number, or 0, and S is any number less than 1. Okay. Oh, no. I was going to say this is not, okay, that's not what it meant. 0 is less than or equal to both R and S, and R and S are both less than or equal to 1. So in other words, your R and your S are less than or equal to 1. Well, what do we mean by that? It's sort of like we had here, but now we're not letting R be negative like it was here. This time R and S are between 0 and 1. Here's your vector V. There's your vector W. Here's the sum of vector V and W. The linear combinations for all RV plus SW for R's and S's, both between 0 and 1, that's what this is saying, is going to be this thing in here, inside that parallelogram. See, if you let R or S be greater than 1, then you would be spanning some space bigger than this, okay? So here's a new definition, the spanning, okay? This parallelogram spanned by V and W. In other words, that defines V, W, and V plus W is going to define that parallelogram. And every vector is a linear combination of those two with R and S both between 0 and 1 is going to fall inside that area, you might say. All right, now Emmanuel is in linear algebra, and in about a month or two, we will be doing spanning and that stuff here. Before that, we'll be doing linear combinations. So if any of you take linear algebra, I think you're the only one here that is in that. Oh, yeah, Marcus is in it too. Yeah, you'll be seeing this also in linear algebra. If y'all take linear algebra, you'll see it also sometime in the future. Okay. Now, let's see what this is. Is this, I think this is example 4. Okay. Okay. And I hate to do this, but I'm going to back up once. This notation here that I was misreading at first, they just put a comment between there. In the new edition, they split that out and say 0 is less than or equal to R is less than or equal to 1, 0 is less than or equal to S is less than or equal to 1, to make it more obvious that's what they're meaning. So evidently they got some guff on that and changed it. Okay. All right, now let's go back to this one. Okay, linear, place of my eye. Express the vector u, which is 4, 4, there it is there, okay, in figure 14 as a linear combination of v, which is 6, 2, and w, which is 2, 4, okay? So we need u to be some linear combination of those two. Okay. Now they've drawn it out, and it's sort of like a, ooh, why, how did they get that? Okay. Or, wow, those are the numbers. Where did they come from? Those are very good questions. Okay. If you express it according to what they said, express u as a linear combination of v and w, that's saying that u is some combination, now, yeah, they're using R and S again, R, V, plus S, W. Okay? And you were told was the vector 4, 4. And this is equal to R times 6, 2 plus S times W was 2, 4. Okay. I admit this is a little messy, but man, it's really hard to. All right, that's a little better. All right. I knew there was something. No, I got it right. Okay. My angle bracket sometimes looks like 7, so don't let that confuse you. It almost caught me. Okay? Guess what? Rather than trying to figure a way to make that work in a geometric shape, just do the math. This tells you that the vector u is express vector u is a linear combination of vector v and w, where vector v is 6, 2, vector w is 2, 4. Linear combination. Just pick two scalars to represent that. And what do you have? Let's write down. I'm going to reverse sides of this, but you do your vector additions and scalar multiplications just like normal. That'd be 6r plus 2s is equal to 4. There's an equation, right? Your x components. 6r plus 2s is equal to 4. Right? I'm sorry, I can't hear. W was 2, 4. They told us that, I think.
Yes.
Yeah, this is example 4. I'm sorry?
Why is there 4, 4? W is 2, 4, right?
Okay. Okay, U is 4, 4. This is U. Yeah, I'm sorry. My tail on my U looks sort of like a W. Yeah, this is U. Okay. All right. Well, by your first components, you get 6r plus 2s is equal to 4. Second components give you what? R, right, is equal to 4 also. Now, I would do a timeout here and say, I can simplify these equations nicely. This is 2 equations, 2 unknowns, have to be solved simultaneously. What's the easy thing you can do to that? Don't tell me a matrix. So we're not going to do that here. But what can you do very easily? Divide each of those equations by 2. The first one becomes 3r plus s is equal to 2, right? Dividing the first equation by 2, right? Goodness, my eye hurts. Divide the second equation by 2. R plus 2s is equal to 2. All right. Now, without linear algebra, how would you solve that? Oh, okay. Which one would you like to eliminate? I would like to do s as well. And how would you eliminate it? Multiply the top equation by -2. And that would produce this as the second equation. Goodness gracious. What would that give you? Minus 6r minus 2s is equal to -4. And add that to this top one. So rather than writing it down again, I'm just going to add them this way. What do you notice happens now? Because you were judicious multiplying the top equation by -2, that sets it so when you add these two together, the S's are eliminated. So that's what we call elimination by addition. So these two go away, and what does that leave you with? Negative 7R is equal to negative 5R. I'm sorry, I can't read. Okay. All right. Negative 5R is equal to negative 2. Is that what you said? That leaves us with R is equal to 2/5. Okay. That looks reasonable. How do we get the S, though? Plug it back into either one of the two equations. That second one looks like it might be the easier one. So plugging in 2/5 plus 2 times S is equal to 2, right? That was your second equation. But the S, yeah, I'm sorry. What would you do to solve that equation? There's several ways you could go. What would be your preferred technique? What's that? Okay, subtract 2/5 from 2. That certainly works, and it works nicely. If you don't like messing around with fractions, which some people don't, Emmanuel loves it, but what you could do is multiply the whole thing by 5. And what would that give you? Give you 2 plus 10s is equal to 10. And then you could subtract 2 from both sides. Oh, man. And that would be 10s is equal to 8. Divide both sides by 10. And s would be equal to 4/5. Or 5ths. And if you'll notice up above, the thing multiplied by R, the V, is 2/5. There you've got it. And what's multiplied by W is S, which is 4/5. And sure enough, that gives you exactly that vector U. Would I even attempt to do that with parallelogram method? No. Using component method and just solving simultaneous equations gives it to you. Pretty straightforwardly, too. Any questions on that? Man. Okay. If I can last another 5 minutes, we'll be through. Boy, I'm feeling lousy. All right. They do have a conceptual insight here. And let's just go through it relatively quickly. I don't think we'll need to spend a lot of time on it. In general, to write a vector U, which is U1, U2, as a linear combination of two other vectors, V, which is V1, V2, and W, which is W1, W2, we solve a system of two linear equations, two unknowns, R and S. Or whatever scalars you want to use. Don't use the same one. Is exactly what we did. On the other hand, vectors give us a way of visualizing the system of equations geometrically. The solution is represented by parallelogram as shown in that figure. That relation between vectors and systems of equations extends to any number of variables and is a starting point for the important subject of linear algebra. Okay. Now, next concept, pretty important concept too. Okay. That's the concept of a unit vector. Okay. Any vector, it has a magnitude or length of 1. It's called a unit vector. Okay? Unit vectors are often used to indicate directions only because the magnitudes are always 1. So you're left basically with the direction. when it is not necessary to specify length. The head of a unit vector E, and there is kind of a reason why they use E here, but I far prefer the symbol U for a unit vector. Maybe it's just me, but it makes a lot more sense. The use of the E basically, I think, comes from the concept of an elementary vector, which you can think of as a unit vector. But usually an elementary vector, in linear algebra we'll get to doing these, and they're very special elementary operations with vectors. So I see no reason to introduce that now, but they do. I like to call it U's, okay? A unit vector U. They're calling a unit vector E, okay? Now, they have one slide or one equation before this, and I think I want to write it for you, then I'll come back and do that one. In 2 space, now this is only good in 2 space. Get this, XY plane. Your unit vector, and by the way, when I write a unit vector, when I write a regular vector, I put an arrow over it. When I write a unit vector, I put a hat on it. That emphasizes to me and to you that's a unit vector. And the unit vector in 2 space, this doesn't work for higher dimension, but for 2 space, it can be written as cosine theta, sine theta. Okay? Now, why is that true? There's a couple of things that feed into that. If you were to draw any old vector, we'll call it E, unit vector E. Now, I'm going to try to draw a pretty lousy looking circle here. This circle has radius 1. So this length is 1, that length is 1, that length is 1, this length is 1, that length is 1. This point out here is 1, 0. This point up here is 0, 1. This point over here is negative 1, 0. And the point down here would be 0, negative 1. Okay. So we've identified just about everything we can about that. There is a unit vector. Okay. Now, sort of standard procedure here is to call this angle theta. And the radius, hypotenuse, is 1. The x component here would be 1 times the cosine of that angle, right? In other words, the cosine of that angle theta is equal to adjacent side, which is, let's call it x, and this y, that would be x over 1, right? So therefore, cosine of that angle theta is x. That's the x component of your unit vector. Okay? Same thing with y. Sine of theta is equal to y over 1. Opposite over hypotenuse, which is 1. So that's just going to be y. So this is your x, that's your y. There is your unit vector E, cosine theta, sine theta. That doesn't work for dimensions greater than 3. 3 or greater. Only works for 2-dimensional space. You can make it work for 3, but it gets a lot more complicated very quickly. Okay, but that's it for 2 space. Okay, now how are we doing? Is it time? Yeah. All right, we'll pick up with this other feature of unit vectors next time. Let's see if we've done enough to get any homework exercises. Hopefully so. I know y'all want some. Yeah, we should be pretty far along. You can do number 1 and or 3, up to you, 1 or both of those. Either 5 or 7, or both. Either 9 or 11, or both. Any of the odds 13 through 17. I would say any of the odds 19 through 27. Any of the either 29 or 31 or both, if you choose. Any of either 31 or 35 or both, if you choose. 37 or 39 or both, if you choose. And let's stop there and we'll pick up the rest of those later. All right. Sorry, folks, I didn't get any further, but man, I'm feeling really lousy. Okay, but we will pick up and go from there. So, in the